Okay, so welcome to Math 310, Introduction to Modern Algebra. So this is lecture 2. So what I want to do today is review some material that you've hopefully seen before. Not sure if I can review material you haven't seen before, but this is hopefully stuff you've seen in some of your other classes. So we're going to go a little bit quickly. If you have any questions, I'll stick around afterwards, and I'm happy to go over things in greater detail. I had mentioned, always have a plan B. We had that on day 1 where the computer was not projecting. We almost had that today where I got a flat tire driving through construction because not everybody knows how to clean up screws. Any hockey fans here? Okay, I'm not a huge hockey fan, but they are phenomenal at having a plan B. So it is a requirement that at every professional hockey game, there is somebody in the stands who at a moment's notice can go in and play goalie for either team. And so a couple of years ago, Toronto was playing Carolina, and the goalie for Carolina goes down, so the backup goalie goes in, and so they alert the guy in the stands, we don't think anything's going to happen, but, you should probably suit up just in case. And so he drives the Zamboni. He occasionally does practice for them. A couple of minutes later, the next goalie for Carolina goes down, and he finds himself the oldest person ever to be starting their first game as goalie. He quickly lets in 1 or 2 goals, but then settles down and actually plays really well, shuts out Toronto for the rest of the game, and gets the win. And so, it's unlikely, but there's only so many people you can count. You always want to have a plan B. And so this is just really good advice. This is why I bought his shirt from the Carolina Plains. My wife's a professor of marketing. People in Carolina knew a good thing when they saw it. Let's get some merchandise out of this. But when you're going through things, always think about what could fail. How bad is it for you for that to fail? And what can you have as a backup? Okay, so for today, I want to talk a little bit about some terminology at first, which is always so exciting. All right, so there's some notation that we need to do. Function is 1-to-1 or injective. Have people seen that notation before? Okay, so 1-to-1 or injective. That means if f of x equals f of y, then x equals y. Does anybody know what it is if you have IFF? What IFF is? Yes. If and only if. I could say that this is an if and only if. Well, if x equals y, it's really not that surprising that f of x equals f of y. Yes, it's true. This is an if and only if, but one direction is so trivial, it's not really worth mentioning. So can somebody give me an example of a function that's injective? Always be able to give examples of things. So distinct inputs go to distinct outputs. What would be an injective function? Excellent. Whenever possible, be a smartass, right? When you're asked for an example, go for the simplest thing that you can think will work. Can you give something a little bit more complicated?
F of x equals x minus 1.
Good. And you've got to be a little bit careful always about what space is this defined on. So if we look at functions defined on spaces where maybe we have a clock, do we have to start worrying if we subtract that maybe? So an example that's non-injective. Could I do f of x equals x squared? Why not? Put an example that's non-injective.
You do f of -2 and f of 2, you'll get the same answer, which does not imply that -2 equals 2.
Right, so I'm looking for an example of a function that's non-injective.
Oh, okay.
As long as my space is not just, say, the inputs are just 0 and 1. Right? If my input is just 0 and 1, then this actually would be injective because my only 2 inputs are 0 and 1, and 0 squared is not 1 squared. But if you consider the input to be the real numbers, the integers, things like that, then this would be a good example of non-injective. Onto or surjective means all outputs hit. You might remember, sometimes they talk about the difference between the range and the image of a function. Does that sound vaguely familiar? And so if you redefine things, you can always make something surjective. So I could have a function f from maybe some set s to some set t, or I could consider it from some function, from some set s to the image of s under f. And clearly, in the second case, it's going to be surjective. Because now everything is going to be hit because I've redefined my outcome space to be the things that are hit. So it's really not that much of an accomplishment to be, onto in that case. So depending on what I give you, if I give you f of x is x squared, it's onto as a function from, say, r to the non-negative integers, but not from r to r. Doesn't want to let me finish writing the letter. Again, you just have to be a little bit careful at times of which are, okay. And then the last one is an equivalence. So this is a reflexive symmetric transitive relation. So reflexive means x is related to x, so you're related to yourself. Symmetric, x related to y implies y is related to x. And transitive, if x is related to y and y is related to z, then x is related to z. You give me an example of a equivalence relation. So I'm going to put you on the spot because you've already given me the answer earlier today. What's the example?
The equal sign.
The equal sign, the identity, right? So if our only examples are the identities, it's going to be a really boring semester, right? Can you give me a non-trivial example? I will try to remember to bring batteries. There's a clock. So if you think about the clock actually gives us a non-trivial example. We could say two numbers are equivalent if they differ by a multiple of 12. Will you be equivalent to yourself? Yeah. If you're equivalent to y, is y equivalent to you? Yeah. And then the last is if the difference between x and y is a multiple of 12, and the difference between y and z is a multiple of 12, then the difference between x and z is a multiple of 12. So it's a nice exercise, go through and put in the details that a good example is x is equivalent to y if x minus y is a multiple of 12. So go through and show that if we take a relationship to be you differ by a multiple of 12, then you're equivalent. Think of an equivalence relation as saying which things really matter. How many of you are familiar with the classic physics experiment by Galileo that the mass does not really impact how long it takes an object to fall near the Earth's surface? People are familiar with going up at the Tower of Pisa, took two spheres, dropped them. What were the colors? You don't know the colors? Jeez, what's education coming to these days? Why don't you know the colors? Should we know the colors? Is that important in this experiment? Why not? Yeah.
They didn't have any impact.
So do you think that the speed, the time to hit is independent of color? So when we're trying to look at our objects, if they differ by color, that's fine. They're not the same object, but they are equivalent maybe in the properties we care about. It is possible that color could matter. And here's why. Maybe one object is white, one object is black, and they sit in the sun for 8 hours before we drop them. So they're now at different temperatures. And so maybe the color itself doesn't matter, but it could lead to some other property. So you really want to think about whenever you're studying, which things really matter. The point of equivalence relations is to say, for what we're studying, I don't care about every single property of the object. I can simplify things a little bit. If you try to model things in the real world, there are so many things going on that if you try to have a complete model, it's just not going to be practical. So the goal is to try to find which things truly matter. And for a lot of things we're doing, we don't necessarily care about every single property of the object. We only care about a couple of key properties. Okay, how many of you have not seen proofs by induction before? We're going to do a couple of examples today. Okay, so everyone has at least seen proofs by induction. So I'm going to go through this, somewhat quickly. There's lots of different things you can do by induction. Some of the standard ones that are required to prove is 1 plus 2 plus 3, all the way up to n is n plus 1 over 2. So this is one of the standard things to prove by induction. There's a nice proof of this without using induction. And the story goes that when Gauss was 5 years old, and again, I have no idea if the story is true, but it's fun to share. His teacher was having just one of those days. And someday, I know a lot of you are thinking about becoming teachers, you will have one of those days when you just can't deal with the brats. And so the teacher said, add up the numbers from 1 to 100. And when you give this to 5-year-olds, that should buy you some time. And Gauss immediately said 5,050. And what Gauss noticed is if we call this sum Sn, if I write the numbers in reverse order, does it change the sum? No. And so now if we add, each column is going to give us n plus 1. And so that's going to be twice Sn. So therefore, how many copies of n plus 1 do we have? No, of n plus 1 on the left-hand side. And so we have n times n plus 1 equals 2Sn. So using division, we get Sn is n plus 1 over 2. So we'll prove this by induction in a moment. It's worth looking at this for a couple of reasons. One, it shows you that frequently in mathematics, there's more than one way to do something. There may be a way that's better for a specific problem, or there may be a way that generalizes better for a later problem. Sometimes you have methods that are highly tailored to the specific problem you're looking at, and they're not really good in general. Building on our success of the sum of the first powers of integers, I'm really priming you. What should we study next? Yes. Sums of squares. So would a trick like this work? Not as well. 1 squared plus n squared is not going to be the same as 2 squared plus n minus 1 squared. But you could ask, what do they differ by? And so could you use a trick to do sums of squares? Maybe knowing this result. And so you always want to see how far can I push it. So I know how to add sums of first powers. If I want to try to do sums of squares, it's not going to quite work out, but there's going to be some extra gunk. Maybe that extra gunk will be related to this, and I can then use my known result for this to now get sums of squares. And if that works, what could I try next? Sums of cubes. And maybe sums of cubes would involve cubes, and then maybe second powers and first powers, which I know. And then maybe I could just keep whittling away like this. And for any specific power, I might be okay, but it may not be easy to figure out what is it going to be in general. So when you're trying to prove things by induction, if you know what the answer is, it makes the induction a lot easier. Right. So induction, so we just did, it was n plus 1 over 2. We have some statement P of n. We're trying to show that P of n is true. We could check this for lots of choices of n. Maybe we check it for a million choices of n. The more you check, the more confident you are that it's right, but that's not a proof. So can somebody, let's just make sure everybody's awake right now. What is 16 over 64 in lowest terms? 1 over 4. Okay, excellent. We have at least one person awake. 19 over 95. 19 over 95? Yep, does that reduce? Yes. 1 over 5. Let's do two more. 49 over 98. Does that reduce? Half, okay. And I've got space to do one more. Let's do 12 over 24. What do you think it is? I get a fourth. I was up late dealing with the car and then got up early to deal with the car again. So I may be doing something wrong. Do other people get a half or a fourth?
12 times 2.
All right, so 12 times 2 is 24. Okay, that's not how I do it. 16 over 64, I cancel the 6's and I get 1/4. 19 over 95, I cancel the 9's and I get 1/5. 49 over 98, I cancel the 9's, I get 4/8, which reduces to 1/2. So the way you divide the ratio of two two-digit numbers is if the opposite main diagonal is the same, you can just cancel them. And I've got 3 data points, right? This is one of my favorite examples. You have to be careful. If you do it at too young of an age, you'll go, oh, okay. So be very careful in using this, but it's a great example of how a pattern can hold for a while, but then stop. There's another way to do this if you want to be, and again, since we have people who want to be teachers, I want to try to give you a couple of things that you can use as teachers. Another thing you could do is keep that in strategic reserve. Just give 2 examples, and then if somebody disputes 12 over 24, say, all right, let's choose another fraction and just test and see if I'm right. Let's choose, oh, I don't know, 19 over 95. There's a nice polynomial whose first 41 values, when you evaluate it, f of 1, f of 2, f of 3, they're all prime numbers. And so it works for like the first 41 values. So what you could do is show for the first 36, 37 values that it's prime. And if somebody doubts you, you've got a few left in reserve. Okay. This is one of the most common mistakes people make, is they show something holds a couple of times and they think it always holds. You have to be careful. You have to give me a reason why something is true. Okay, so here's how induction works. We have 2 statements. P1 is true. This is called the base case. And then whenever Pn is true, then Pn plus 1 is true. If we can show both of these statements, then we're done. Sometimes people start counting at 0 rather than counting at 1. Doesn't really make much of a difference. Okay, so again, this should hopefully be review, base case inductive step. And then why does this imply that it holds for all n? Well, if P1 is true, now just take n equals 1, and the second statement becomes whenever Pn is true, then Pn plus 1 is true. So P1 true implies P2 is true. Notice that this doesn't say Pn is true, it just says whenever Pn is true, then Pn plus 1 is true. Since we know P1 is true, and we know P1 true implies P2 is true, we now know P2 is true. Now what value should we take for n? I'm sorry? Nope. I need a value for n. We just showed that if P1 is true, we now know P2 is true. What now should I take for n? 2. And then I know P2 is true. I know P2 implies P3 is true. I know P3 is true. Now what value should I take for n? 3. And you just keep marching down like that. Okay? And so now we've got P3 is true. We then take 3, and then we get P4 is true. So sometimes people draw this as the ladder. Sometimes they do it as dominoes falling down. I know P1 is true, that gives me P2 is true, that gives me P3 is true, and I just march down like this. So if I can prove these 2 statements, I know it will be true for all n. Okay, so let's look at the sum of the first n integers. We're going to show it's n plus 1 over 2. This is one of the most standard proofs by induction. So if you've seen proofs by induction, almost surely you have seen this one. So first we prove P1 is true. All right, well, that's not that hard. We just have to show 1 equals 1 times 1 plus 1 over 2. And then we have to show that whenever Pn is true, Pn plus 1 is true. Okay, so as I remarked, the base case is quite straightforward. We just plug in 1 and substitute. Now, if you want, you could actually try and check, is it true when n equals 2, when n equals 3, when n equals 4? We don't need to do that. If we can show Pn implies Pn plus 1, we're done. Sometimes it's not bad to do a few other cases because A, maybe it's wrong, and then you'll quickly find that out. Or B, maybe by doing a few more interesting cases, you'll get a sense of how the argument goes, and that will give you an idea of how to try to prove things. Okay, so again, you can build up some intuition. It's not necessary, but it's not a bad idea. So why not? Let's check, does it work for 2? Does it work for 3? So doing very straightforward algebra, yes, it works. Yes, it works. Okay, great. So now, how do we proceed? This is the hardest part in mathematics, is trying to figure out what's the best way to attack a problem. This is one of the advantages, computers have over us. They can try millions, billions, soon trillions of possibilities. They've got it now so that your computers can use machine learning to figure out how to solve a Rubik's Cube just by playing with it and just turning it. And eventually they start to realize, here are sequences of moves that do things. I will risk asking this question. You have a baby, the baby is crying, what do you do? And I will then share the worst answer I've ever gotten to this question in one of my classes. Baby is crying, what do you do? Come on, people, give me a suggestion. Yes. Good, give it a basketball. The worst answer ever was shoot it. Yeah, that should not be the first, nor should it be the second or the third or any of the answers. Give it a pacifier, excellent. What else could you do? That's all we can do is give the baby a pacifier. Yes.
Rock it.
Lock it, good, cradle it. What else? Feed it, good, what else? Ignore it, yep. You go to another room, yep, absolutely. Change the diaper. Right? There's lots of things you can do. After a while, especially if it's the same baby again and again and again, you start to notice the differences between the different types of cries. This is the I'm hungry cry. This is the I want to be held cry. This is I have a diaper that needs changing cry. I don't think you'll ever hear the I need to be shot cry. But when you start to hear these different cries, you know how to respond faster. You've seen this before. In a calculus class, when you have integrals to do, you start to look at things and you're, okay, this is going to be a trig substitution, and I'd rather do cosine than sine. This is going to be an integration by parts. This is going to be, oh dear God, they gave me a partial fraction. Damn it. Okay. But you start to recognize which one it is. And if you're not sure, you just go down the list. You just keep trying. And the more experience you have, the faster it is to go down the list. So when I'm trying to prove something like this, how do I prove things by induction? I get to assume Pn is true, and I want to prove the statement Pn plus 1. All right, so, well, the statement Pn that I get to assume is true is the sum of the first n integers is n plus 1 over 2. I want to show that the sum of the first n plus 1 integers is something. G, if you look at the beginning of what I need to prove, you can see quite clearly the sum of the first n integers, which by assumption we know. So this suggests how we should attack the problem. Let's look at the left-hand side of this. By assumption, we know what this equals. Let's put that in, and then let's do some algebra. And that's exactly what you do. So we notice that what it is, we plug that in, and then we will get n plus 1 over 2 plus n plus 1. Well, they both have an n plus 1 that I can pull out. It's n halves plus 1. So when you do the algebra, and when everything settles, after you do all the fractions, you're going through excruciating detail, you end up getting exactly what you want. And I've just written the last one as n plus 2. You could write this if you want as n plus 2 is n plus 1 plus 1. So it's exactly the form we want. So this is a real follow your nose proof by induction. If I gave you the sum of squares, if I tell you it's n plus 1, 2n plus 1 over 6, it's essentially the same proof. All that changes is the algebra. If I tell you, here's the formula for sum of cubes or fourth powers, straightforward. You just plug in and then just do basic algebra. If I don't tell you what the right-hand side is, now it's much harder. There is a couple of ways to do it. Probably the simplest if I tell you a specific number. So give me a number. Give me a nice integer.
6.
6, okay. If you look at this, you should notice that this is a polynomial in n. What's the degree of the polynomial?
3.
3. And I have sums of squares and the polynomial was 3. When I had sums of first powers, the polynomial was 2. If I have sums of 6 powers, what would you expect? Polynomial of degree 7. I could start the sum at 0. And if I start the sum at 0, then you might think, if n equals 0, then I would just get 0. So maybe my polynomial should be multiple of n. And if you remember your calculus, which is a prerequisite for the class, right? 0 plus 1 plus ... plus n, and let's do this to the 6th power because you liked 6. That should be approximately the integral of x to the 6 dx from 1 to n, right? Which would be x to the 7th over 7 at 1 and n, or n to the 7th over 7 minus 1/7. And again, I'm just trying to go for a ballpark answer. But this is the Riemann sum. If I'm summing my function at 0, at 1, at 2, at 3, that's like integrating the function from 1 to n. I'm not worrying about, or maybe I should be integrating from 0, so let's make it 0. Now make things a little bit nicer. So is everybody fine with that's a reasonable approximation? That it should look like n to the 7th over 7. So over here, this should look like n cubed over 3. Oh, n and 2n, that's 2n cubed over 6. Yes, that actually is an n cubed over 3. So this looks reasonable. So by looking at this, if you think that it's going to be a polynomial of degree 7, we actually have an idea of what the leading coefficient is. We have an idea of what the constant coefficient is. How many coefficients does a polynomial of degree 7 have? How many coefficients do you need to specify a polynomial of degree 7? Yes, you need 8. I already know 2 of them, so I need 6 more. So I could evaluate this at maybe 6 different values of n, and then try to figure out which polynomial would actually have those. And then that would tell me what to do for the induction. So there is a way to do that. I have an incredibly painful proof of how to do this using calculus and doing differentiation. So if anybody's interested, I will try to remember to share that proof later. I was able to get it to work for the first powers and the second powers. You give me any finite power and I can make it work, and the algebra becomes overwhelming. But it's a non-standard use of L'Hopital. So I like, you've made it when your name is a verb. So, it's an interesting argument. But do we all agree that this is not going to be hard to prove by induction? As long as I tell you what to prove. All right, so I'm not going to go through the steps, but the details are here. Here's another fun one. The sum of the first n odd integers is n squared. And it's just a question of how do I want to write my odd numbers? Do I want to write them as 2n plus 1 or 2n minus 1? If I write them as 2n minus 1, the first odd number comes from n equals 1. The second odd number comes from n equals 2. That seems to be a nice way to write it. If I wrote it as 2n plus 1, then the first odd number comes from n equals 0. So just trying to have good notation. I am a huge fan of take the time to have good notation. Really think about what you're going to be doing. And so again, this is not that bad to do by induction. I'm not going to go through the details. And then just, this is a great example of one that can be done by ways other than induction, by just writing circles for 1, for 3, for 2n minus 1, and just keep adding more rows and columns. So if I just have one odd number, it's 1. If I have 2 odd numbers, it's 1 and 3. And when I put the 3 in like an L shape, that now gives me a square. When it's 5, it's going to give me another, and it's going to now make the square be 3 by 3. So this is a nice geometric proof. All right. I'm not going to go through this one. I'll leave this one in the notes. This one is a little bit more non-standard. 133 is always going to divide 11 to the n plus 1 plus 12 to the 2n minus 1. And so what's nice about that is it's not immediately clear how you're going to do the induction here. So everybody close your eyes for 2 seconds, please. Okay, that way I was able to just show the slides. And so if people pause it, the slides are there. Okay, so this is a math department. This is a math class. We like to prove things. Unfortunately, most of the time, we're not able to prove things exactly. Frequently, that's not a big deal. We're often able to calculate maybe the main term and a small error. Imagine you're Jeff Bezos, and you're told that there's an accounting error. We're really sorry. You have $1,000 less than we thought you did. What should his response be? Exactly. Whatever, slap you, you're fired. Don't ever bother me for this again. I'm going to waste more time on $1,000, relative to how much I have. This is within the margin of error. Now, for a lot of us, that could be significant. So you always want to be looking at things in context. If you have things that are measured in the scale of billions, $1,000 is insignificant. You want to get a sense of what is the main term, what is a lower term. We calculated the sum of the first n integers is, n plus 1 over 2, or n squared over 2 plus n over 2. Is this reasonable? But what this is saying is that it's growing like something of order n squared. It's 1/2 n squared, but it's really growing like order n squared. What does this mean? If I were to increase n by a factor of 10, the sum would increase by roughly a factor of 100. If I would increase n by a factor of 6, it would increase by roughly a factor of 36. For large values of n, the n halves is much, much less than the n squared over 2. So for a lot of things, can you just look at it and get a sense of the size? So over here, let's try to get upper bounds and lower bounds. So I do not care the best upper bound right now. I do not care for the best lower bound. Just give me an upper bound that you are willing to stake your life on is correct. That's going to be so obvious, I can't dispute it. I mean, if you say n squared over 2 plus n halves, yes, that's an upper bound, but you can only justify that by doing some good math. Give me a trivial upper bound that just looking at this, is going to work. Trivial upper bound for the sum. Infinity, right? Absolutely. You want to be safe? I'm summing a finite set of positive numbers. It's clearly going to be less than infinity. You are safe. You do not die. Can somebody give me a better result than infinity? I notice they can't just do infinity minus 1 because that's still infinity. So can somebody give me a finite upper bound that you're safe? This is definitely going to be less than. Question? Question? So when you look at this, how many terms do we have?
I say n to the power of n.
So you could do n to the n. Why would n to the n work?
Because it should always be greater because there are terms that are less than n.
Okay.
Sum.
So n to the n would work, but there's something a little bit better than n to the n that's on the same spirit.
N squared?
N squared. Why would this be less than n squared?
Because n squared is n plus n plus n. And
Right. So if I replace everything with an n, I've only made it larger. So clearly, it's going to be at most n squared. What about a lower bound? Give me a lower bound for this sum that is going to work. Give me a stupid lower bound. Negative infinity, there you go, right? We're summing a bunch of positive numbers. It's clearly going to be greater than negative infinity. All right. And again, they can't do negative infinity plus 1 on you. They've got to do something significantly better. Can you give me something better than negative infinity?
And
Can you give me something worse than n? 0 or 1. Right? Because if we just look at the smallest term, it's at least 1. Better to look at n. And so unfortunately, when we do something trivial like this, our lower bound and our upper bound are different orders of magnitude. So when we're looking at this, it's not immediately clear what is going to be the true rate of growth of this function. So we need to come up with either a better lower bound or a better upper bound. Okay, so this is just quantifying, what we were doing a moment ago. You're putting in every term in the sum is at most n, every term in the sum is at least 1. The number of terms is n, upper bound is n squared, lower bound is n. There's a huge, huge gap. And so here is a way we can do things a little bit better. And so I've written it down here, but I'll write it out over here. We have 1 plus 2 plus ... plus n halves plus n halves plus 1 plus n. So I'm going to split it in half. In the first half and the second half, each term in the first half is at most how much? At least 1. So it's between 1 and n halves. And in the second, what is it between? N halves. Technically, n halves plus 1, but I don't really want to write the plus 1, so let's just do n halves and n. So we've taken our problem and we've made it into 2 smaller problems. Now we can get an upper bound from each one. So the upper bound, we have n halves terms that are at least n halves from the first, plus n halves terms that are at most n from the second. So that's n squared over 4 plus n squared over 2. So that should be 3/4 n squared. And the lower bound, we have n halves terms that are at least 1 plus n halves terms that are at least n halves. That's going to be n squared over 4 plus n halves. So notice, just by doing this simple calculation, we now have that it's somewhere between n squared over 4 and 3n squared over 4. So we have a good sense of the size of the answer. Now the question becomes, shampoo mathematics. Can anybody tell me what they say on shampoo bottles? The instructions. You haven't read the instructions on shampoo? Oh my God, this is scary. Lather, rinse, repeat. Right? Now, if it's lather, rinse, repeat, do you repeat once or do you repeat forever and ever and ever and do nothing but shampoo your hair? We broke it up into 2. What could we do next? 4. And so it might be nice if you start off with n as a power of 2, so things split nicely. And so what you could then do is break it up into 4s, into 8s, into 16s. And does this converge? Is it converging to at least the main term going to n squared over 2? So again, I'm happy to just put out a lot of these things for you to think about. If you want to write them up and share them with me, please go ahead. Can you keep doing this and get that the main term is going to look like n squared over 2 as you keep doing more and more of this? We talked about the factorial function before. So how many of you have heard of Stirling's formula for n factorial? Okay. I will try to remember to put my hand up when I actually never took abstract algebra as an undergraduate. Long story. So Stirling's formula is a way to estimate how large is n factorial. And you can do tricks like this to get a good feeling of what it is, but it's hard to show that it converges. All right. Talked a little bit about interpolating, so I don't really want to say much about this. Okay. Is there a person here who is brave enough to volunteer and has an identification card on them. Driver's license, Siena college ID, name that's somewhat easy to pronounce. Any volunteers? Okay. I see an ID. Okay. We are going to prove that everybody is named Elizabeth in the world. Is anybody suspicious of this? Yes, Elizabeth, why are you suspicious of this?
My name is not Elizabeth.
Are you sure?
I believe I am.
I mean, I realize my stock is a little bit low because I thought 12 over 24 was 1/4, but I will try to prove that your name is Elizabeth. All right? So here's my statement. Pn, in any group of n people, everyone has the same name. Different groups of n people can have different names. But my statement Pn, which I'm going to prove by induction, is that in any group of n people, everybody in that group has the same name. So I must show two things. I must show the base case, and I must show the inductive step. Does everyone agree that if you have a group of just one person, that everybody in that group has the same name? We agree that that is clear. So now I have to prove the inductive step. If everyone in a group of size n has the same name, then everyone in a group of size n plus 1 has the same name. And if I can do that, then by induction, we're done, and everybody is named Elizabeth, because I know at least one person is named Elizabeth. All right. So the base case follows immediately. Okay. So here, using some images I drew from the web, is n plus 1 people. And I'm going to show that everybody has the same name. Can somebody give me a group of n people from these n plus 1 people? I need to choose n people. Give me a nice way to choose n people. Can anybody give me a set of n people from n plus 1 people? You have to give me a rule to choose who my n people should be. Okay, so probable Elizabeth suggests we take 1 to n. Okay, and that would be a group of n people, and they all have the same name. Can someone else give me another group of n people? I need another group of n people. 2 to n plus 1, right? And they would all have the same name by the inductive assumption. I get to assume Pn is true. Well, everybody in the first n, they all have the same name by deductive assumption. Everybody in the last n has the same name by deductive assumption. And peoples 2 through n are in both groups. So everybody in the first group has the same name as person 2. Everybody in the last group has the same name as person 2. Therefore, everybody has the same name. And everybody's named Elizabeth.
How would we prove n plus 1 has the same name?
Well, because we get to assume that the statement Pn is true. We assume that whenever we have a group of n people, they all have the same name. And so we showed, P1 is true. We proved the base case, right? And then we showed, look, consider a group of n plus 1 people. By the inductive assumption, the first n people all have the same name. The last n people all have the same name because those are groups of size n. There is a person in both groups, person 2. So everybody in the first group is the same name as person 2. Everybody in the second group is the same name as person 2. So everybody has the same name as person 2. So in any group of n plus 1 people, everybody has the same name. And given that we know at least one person's name is Elizabeth, we now know everybody is named Elizabeth. You disagree? Then where's my mistake?
I see your mistake right now.
Because the inductive step is like a proof statement, but the assumption is false here, yes. Or something like that.
I prove the base case, and then when I'm doing the inductive step, I don't need to know that Pn is true. I get to assume Pn is true, and then I use it to prove Pn plus 1 is true. I showed that if Pn is true, Pn plus 1 follows. So is everybody named Elizabeth? Yes. So I could have included in the prerequisites that you must be named Elizabeth to take this class, which really wouldn't be a hard prerequisite to fill. So what is the issue? So you've got everybody with the same name. The issue breaks down. Imagine n equals 1. Then n plus 1 would be 2. And there's no person in common. When I was drawing these pictures and showing, look at all these people in common, that only holds if n is a large number, like 2 or 3. When n equals 1, it breaks down. When n equals 1, there's no common person between the two. This is somewhat similar to maybe some of the old geometry proofs you saw years ago, where you have to be careful that if you draw a triangle, that you've truly drawn a generic triangle and are not using specific properties of the realization you drew. And so over here, if you want to view it as a staircase, we're missing P1 implies P2. If in any group of 2 people, everybody had the same name, would everybody in a group of 3 people have the same name? Yes, because then I could do 1 and 2 have the same name, 2 and 3 have the same name, so everybody has the same name as 2. So I do know that P2 implies P3, and I know P3 implies P4. I'm just missing a step. And this is why it might be the case that everybody's named Elizabeth, but this is not going to be the way to show that. So this is not a proof that is correct. There is an issue here. There's a lot of false things you can prove where the inductive argument works from 2 on up, but there's a gap from 1 to 2. So the danger is when you are trying to prove something that you might put in additional properties, additional assumptions that are not necessarily there. And I will give another example of that later today. But again, one of my goals for the class is to really emphasize methods, techniques. How does a mathematician think about problems? What are the dangers? What are the pitfalls? It is so easy to accidentally assume more than is there. Okay, hopefully everybody's seen Pascal's triangle. So there's a lot of beautiful relations among quantities. So as you go down on the left or the right, you have ones along the diagonals, and then every number is the sum of the number above and to the left and above to the right. If you wanted to, another way of viewing it is you could also put in like infinitely many zeros in both directions, and then everything would propagate from that if you want to do that. So there's lots of properties you can prove about the elements of Pascal's triangle. Why do we care about this? Well, if you want to expand x plus y to the n, when you expand it out, the coefficients are coming from Pascal's triangle. This was extremely important in calculus. If you wanted to calculate the derivative of x to the n, you had x plus h to the n, and you needed to expand that out. And this was one of the great applications of this. So we can keep going, further and further and further. And one of the ways to see what's going on is there's many interpretations. If I have x plus y cubed, all of my terms are going to involve x's and y's. And the sum of the powers of x and y's has to add up to 3. So what I'm really doing when I'm expanding it is I've got to figure out what's the coefficient of x cubed, x squared y, xy squared, and y cubed. Well, if I have 3 factors and I have to choose x every single time, how many ways are there to do that? It's 3 choose 3. If I have 3 factors and I want to choose x twice and y once, it's 3 choose 1. So does everybody agree that I can view the 3 as 3 choose 2? A better way of viewing it is 3 choose 2 times 1 choose 1. I choose 2 of the factors to be 3. I'm sorry, 2 of the factors to be x, and then I choose 1 of the remaining factors to be y. Well, what's 1 choose 1? How many ways are there to choose one object from one object? 1. So because it's 1, we frequently don't write it, which is kind of a shame because it then hides what's really going on. If I had x plus y to the 4th, it would really be 4 choose 4, x to the 4th, y to the 0, plus 4 choose 3. I'm sorry, this should then be 0 choose 0. I mean, that's kind of scary. And then 1 choose 1, x cubed y, plus I choose 2 things to be x's, and then of the 2 remaining things, I choose both of them to be y's, x squared, y squared, and so on and so on and so on. All of these second factors are just 1. And because they're just 1, we don't write them. But really, that's what's going on. If I have 6 factors and I choose 2 of them to be x's, then the remaining 4 factors are all chosen to be y's. And that's going to be a 4 choose 4. I'm not going to bother to write this. So the identity is each number is the sum of the number above to the left plus above to the right. This is just going through in details if you wanted to. Lots of ways to prove things. You can talk about choosing things in combinatorics. Another way to do it is I could write x plus y to the 6th as x plus y times x plus y to the 5th. I know what x plus y to the 5th is and expand it, and I multiply that by x, I multiply it by y, and I add them. And you can go through, and this is going to give you a sense of where Pascal's identity is coming from. To get to the next level, I'm summing 2 things from previous levels. So this is another way to just see what's going on without telling the whole story. Okay, the small limit can expand directly. People frequently have not seen proof by story. How many of you have seen proving combinatorial relations by telling a story? So what you basically do is whatever you want to prove, you show that what you want is equivalent to something else, and that something else is easier to prove. So can somebody give me the name of a good college? This shouldn't be that hard. Nobody knows the name of a good, sorry. Good university, I forgot. It's after the first. Good university. Name of a good university. Bill, you want to go with Harvard? All right, we'll go with Harvard. I even looked up who the rivals was. We'll have N people from Harvard, and we'll do my alma mater, Yale. We'll have 1 person from Yale. I want to form a group of N plus 1 people. Actually, we're not going to have Yale in crimson. We'll have Yale in blue. How many ways? Let's see. Let's see. We have N plus 1 people. We want a group of K plus 1 people. What are the number of ways we can do that? How many ways can we get a group of K plus 1 people from these N plus 1 people?
Is K smaller than N?
K smaller than N. How many ways can we do this?
N choose K.
Why N choose K? We have N plus 1 people, and we want a group of K plus 1 people.
N plus 1 choose people.
N plus 1 choose K plus 1. This is the definition of the choosing function, right? I have N plus 1 people I want to choose. Okay, there's 2 cases. Case 1, happily have the Yale person. And what's case 2? Don't have the Yale person. So in this case, we can calculate how many people do we have from Harvard? How many people do we have from Yale? Clearly, we have 1 person from Yale in the first case and no from Yale in the second case. In the first case, how many people from Harvard must we have if we want to have K plus 1 people total? K. And in the second case, how many must we have? K plus 1. How many ways are there to choose K Harvard people from a set of N Harvard people? And choose K. And how many ways are there to choose one Yale person from a set of one Yale person? One, choose one. And then we have, for the second case, it's N choose K plus 1 times 1 choose 0, and that's going to be N plus 1 choose K plus 1. There is Pascal's identity. What's really going on in Pascal's identity is we really have two extra factors of 1. And when you put those in, things actually look a lot better. The tops, you can't just add really the tops of binomial coefficients, but N plus 1, N plus 1, N plus 1, all the tops add up to N plus 1. All the bottoms add up to K plus 1. So again, part of this is to just give you a sense of where the binomial theorem is coming from. If we have time, I'll do one more proof by story. I'll ask someone else for the name of a good institution. Anybody want to give me the name of a good unit? Yes. Princeton. Okay. We'll have N people from Princeton. So at Yale, we were taught Harvard sucks and Princeton doesn't matter. There are shirts that actually say this, which I don't like because they actually write Princeton on them and acknowledge Princeton's. I do have a degree from Princeton math, but that's different. So who's Princeton's basketball rival? We'll see who knows sports. The excitement of Ivy League. UPenn is their rival. So we'll have N people from Princeton, N people from Penn. Okay. And let's consider the sum K goes from 0 to N of N choose K squared. It turns out that there's a nice answer for what this sum is. Anybody ever read Dr. Seuss? Do people know the Sneetches? There are two types of Sneetches, those with stars on their bellies and those that don't. And what do you think they learn by the end of the book? What do you think they learn about whether or not it matters if you have a star? It doesn't, right? I mean, this is Dr. Seuss, right? It doesn't matter, but it takes us a couple of pages and a lot of trouble before they realize it doesn't really matter if you have a star or not. If I'm choosing K Sneetches from N to get a star, and only those K get a star, that's the same as choosing N minus K not to get a star. So we know N choose K is really the same as N choose N minus K. Choosing exactly K people to get something good is the same as choosing exactly N minus K people to exclude. So this sum is the same as the sum K goes from 0 to N of N choose K, N choose N minus K. So does everyone agree that these two sums are the same? Okay. Anybody know Chekhov's law of literature? Okay, what is Chekhov's law of literature?
If a gun is shown in a prior scene, it must be blue.
Good. If a gun is shown in a prior scene, I think the version I heard is if you talk about the gun in scene 1, it's got to be fired by scene 3. Is that usually you only have so much space. You've got to be very careful. And if you put something in, it's probably important. How did I start this page? We're talking about the sum of N choose K squared, but how did we start this discussion? Choosing university. I have N people from Princeton and N people from UPenn. What the hell does that have to do with looking at this sum? This is proof by story. How can you interpret this? How can you interpret N choose K and N choose N minus K? Given that I've written we have N people from Princeton and N people from UPenn. Yeah, so here we take K from Princeton. And we take N minus K from UPenn. What I'm really doing is I'm looking at all the ways I can get a group of N people from a set of N people from Princeton and N people from UPenn. How many people are there total? Two N. And I'm looking at all the different ways I can get a group of N. Well, that's just the number of ways is just going to be 2N choose N. If I want to choose N people from a set of 2N, there's 2N choose N ways of doing this. How could I do this? I could have no one from Princeton. I could have one person from Princeton. I could have two people from Princeton, all the way up to I could have N people. So this sum, N choose K squared, there's actually a really nice formula for it. As an exercise, it's probably not N choose K cubed that has a nice formula. Try to figure out what might have a nice formula. Okay. Just as long as we're doing some reviews, it's always nice to try to talk about the beauty that's lurking behind mathematics. What I'm going to do is I'm going to look at Pascal's triangle, and I'm only going to care about whether or not you are an even number or an odd number. This is an equivalence relation. For this 1, 3, 17, 20, 25, they're all equivalent, they're all odd. 2, 16, 34, they're all equivalent, they're all even. And wherever I have a odd number, I'm going to put a dot. Whenever I have an even number, I'm going to delete it. And so if I just looked at the first row of Pascal's triangle, I would just get a dot, or maybe you want to call that the 0th row. And then you're looking at the first 4 rows, I would get something like this. And we can go further and further and further. How many of you have seen this before? Okay. And so you can do more and more and more of them, and you start to see an interesting fractal pattern emerge. And so I couldn't find anybody who had done this online, years ago. So I actually wrote some code, and then I tried to rewrite it to do it a little bit more efficiently. Don't know if it'll let me click on it. All right, so I'm not going to bother clicking on it, but if you're interested, you can watch the video. And what I'm doing is I'm constantly forcing my Pascal's triangle mod 2 to be in a fixed finite box. If Pascal's triangle, if I keep adding more and more rows, well, this is going to go off to infinity. So I'm constantly just shrinking things and just keeping things fixed over here. So you can play the video and you start to see the fractal pattern emerge. What I love about this is it shows you that things you've seen before, there's a lot more subtlety going on than you may have noticed. Okay, so I want to do one more topic, and then I want to do some prep work for Tuesday's lecture. So a lot of you have mentioned that one of the things you want to get out about this from this class is about thinking like a mathematician, trying to figure out how do you attack problems. And so I am a huge fan of gathering data. The more data you have, the more likely you are to see what's going on. I will risk doing this at a school that has some religious component in it. If you were the supreme being and you decided to create the subject called calculus, and you are a benign, benevolent being who thinks of all the people who will be worshiping and following you, what would you choose the product rule to be? If you were to make a product rule for your followers to sing your praise of how benevolent you are, what would the derivative of a product be? If you wanted to make a nice, easy rule for calculus students. The product of the derivatives, right? And the students would say, and it was good, right? They would be very happy. This would be easy to remember. And what would the derivative of a quotient be? The quotient of the derivatives. And they would say, this is even better. Division doesn't cause any problems. Wonderful. No, division always causes problems. right? What is the derivative of a product? So the derivative of FG is,
Right, E plus F, right?
yes. And so what we want to do is not prove it, because this is not a calculus class, is we want to see that this is something that's reasonable. So what I want to do is I want to try to predict what the formula for the derivative should be. And again, I'm deliberately choosing something where we know the answer to try to show you a method. If anybody wants to write an article for Math Outreach, I think this would be a terrific topic to write up. Yeah, how do we come up with something like this? So I need to choose two functions, f and g, that not only are their derivatives easy to get, but I can easily find the derivative of their product. Does anybody have a good choice for f of x? Function that's easy to differentiate. X. And give me a good function for g. You could also do x. So I could do x, and their product would just be x squared. Then give me another choice for f. Could do 1. What else could I do? I've done x. What could else I do? Well, no. Well, if I do f of x equals y, that's essentially the same as doing 1, because y is a constant with respect to x. X squared. What else could I do? That's simple. X squared is not that much harder than x. What else could I do? I can do x, I could do x squared, I could do, after x squared would come
X cubed.
x cubed, after x cubed.
X squared.
So want to do x to the m. They're all going to be about the same level of difficulty. And for the other one, I could do x to the n, and then this would be x to the m plus n. And so I could do x and x, I could do x squared and x, but by doing x to the m and x to the n, I can test a large number of cases all at once without making the algebra that much harder. What's the derivative of x to the m? M times x to the m minus 1. G prime of x is going to be n x to the n minus 1. And then f of x, g of x prime would be n plus m x to the n plus m minus 1. Let me just move that over a little bit so that the exponent is a little bit more visible. So I need to somehow get n plus m x to the n, well, I wrote m first, so I should write it this way. M plus n x to the m plus n minus 1. So I want to try to figure out how can I get that using the various pieces I have on the left. I could take g of x equals 1. If g of x equals 1, then f of x times g of x is just f of x. I could take f of x equals 1, and then f of x g of x is just g of x. So by looking at some special cases that can help, can anybody figure out how could I get an x to the m plus n minus 1 from what I have on the left?
X to the what?
On the right-hand side, I have an x to the m plus n minus 1. The power is m plus n minus 1. It makes sense that the derivative should involve f prime, g prime. Because if I take, g of x equals 1, I get an f prime coming in. If I take f of x equals 1, I get a g prime coming in. These are natural pieces to be involved in the puzzle. How could I get the power m plus n minus 1 with what I have on the left? Can you see any way to combine things?
F of x times g prime.
Yeah, so one way is I could do f of x times g prime of x. Is there another way I could do it? And the other way is?
F prime of x.
Yeah, so if I put these two together, I would get f prime of x times g of x plus f of x g prime of x is going to be m plus n x to the m plus n minus 1 when I do all the algebra. Is this a proof of the product rule? No. Remember, 12 over 24 is not 1 4. It holds for a large class of things. And then you could try to see, what if I had f as the sum of two simple things like this? Would that work? And if that works, that would give you a little bit more faith. But what would I need to really convince you that something is here? If no, not by proving it, I'm not going to do that. What would make you more likely to believe this?
An example.
Good. Another example, not involving polynomials. So what's another type of functions we know? Other kinds of functions you've seen. Exponentials, what else? Well, exponentials at e to the x. What else do we have? Trig. And in fact, trig and exponentials are related. E to the I theta is cosine theta plus I sine theta. Let's choose something completely at random. Let's let f of x equals, sine of x and g of x equal cosine of x. Then what's f of x, g of x? That's sine x, cosine x. Does anybody remember their trig identities? What's the trig identity for sine of x times cosine of x? Yes, this is just 1/2 the sine of 2x. And now we can take the derivative of that using the multiple rule. If I give you f of a times x, the derivative is a times f prime at ax. So we can actually differentiate that. So we would get derivative of sine is cosine. Derivative of cosine is negative sine. I like to remember the rule. You have to remember, where does the minus sign go? The minus sign. If you want, think of it as, here's your unit circle. When you're going up like this, cosine is decreasing as you increase the angle from 0. So if cosine is decreasing, its derivative has to be negative. And that's why it's a negative sign. The sign starts off at 0 and the sign is increasing, so the derivative sign should be positive. Okay, what is the derivative of f of x, g of x? So it's going to be 1/2 sine prime at 2x times the derivative of 2x. Well, the derivative of 2x is just 2. The 2's cancel. Derivative of sine is cosine. So we get cosine of 2x. And now when we multiply things, we get f prime g. So we can get cosine x minus sine x sine x. What does that equal? That does equal cosine 2x. If you remember your trig identities, this is so this is another example supporting our conjecture for what is the product rule. So we believe that if I give you f of x, g of x prime, that it's f prime of x, g of x plus f of x, g prime of x. And this works if f of x equals 1 or g of x equals 1. We can test those cases as well. So again, this is not a proof, but it's giving us an idea of what we should try to prove. How many of you remember how you prove the product rule? So the proof is you look at the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h, right? This is how you prove all the differentiation rules. You look at the value of the function at x plus h, you subtract the value at x, and then you divide by h and you take the limit. if you look at this, something should look strange about how this is written. Right? What have I done that you normally don't do?
There's a lot of space.
I have a lot of space. So one of my professors at Yale, Professor Jones, said there's only two things you can do in mathematics. You can multiply by 1, and you can add 0. I said, you know, the log of 1 is 0. There's really only one thing you can do in mathematics. We basically do nothing. A lot of us make a nice living out of doing nothing. So we want to add 0 in a clever way. I have a sense of what the answer is. I have a sense of the answer is f prime of x times g of x. So I've got an f of x plus h. If I wanted to have an f prime, I would want to subtract off f of x, g of x plus h. And then that's going to give me basically, that's going to look like an f prime times g of x plus h. Well, I can't just subtract off something. I have to add it back. F of x, g of x plus h. And now, if I just do some limit properties, this is going to be the same as the limit as h goes to 0, f of x plus h minus f of x over h times g of x plus h, minus the limit. I'm not going to justify all this stuff. H goes to 0. And the next one is going to be f of x, g of x plus h minus g of x over h. And now this part goes to f prime of x. This part goes to g of x. This part is already f of x. And this should be a plus sign. And then the last one goes to g prime of x. So that's the proof of the product rule. You know, it comes down to adding 0 in a clever way. How do you see that? Well, if I have an idea of what I'm trying to prove, I'm searching for an f prime g, I'm searching for an fg prime. That's going to really help me in what goes on. We're going to have to do stuff like this when we get to some of the stuff for groups, when we're doing some of the stuff for rings. So I'm trying to spend the time right now in an area where you have some familiarity. Okay. So I want to end the day with something for you guys to ponder, and then we will play this game on Tuesday. Has anybody heard of the riddle of pirates dividing spoils of war? Okay. Okay. If it is the riddle that you are thinking of, you've become mute.
Great.
Okay. I'm sorry?
Yeah, great.
You become mute. Okay. There you go. So do not search the web. Do not look this up. Just think amongst yourselves. You can talk amongst yourselves, and we will play this probably not for real on Tuesday because there's some real consequences. All right. Before I do the pirate riddle, however, has any of you seen the Wasson 4-card task? So which cards must you turn over to verify the rule that if a card shows a vowel on one face, then it has an even number on the other? So if you have a vowel on one face of the card, A, E, I, O, or U, then the other side must be an even number. Which cards must you turn over? You must turn over E. What else? 4. What else? Anything else?
All of them.
All of them? Are there any cards we don't have to? Let's go one at a time. Do we have to turn over E? Everybody agree we have to turn over E. Do we have to turn over K? Does K have to be turned over? Yes?
Well, I feel like if there was a vowel on the other side of K, it would be a problem.
Good. So this is not how it's normally written, but I love the fact that somebody wrote it like this, because implicit in many people's minds is that each card has a letter on one side and a number on the other. And if you have a K here and the other side has to be a number, then you're fine. Because it's only if you have a vowel do you have to have an even number. So if you assume that there's a number and a letter on each card, you don't have to turn over K. But if you're allowed to have 2 letters, then you would have to turn over K. What about 4? Do you have to turn over 4? It doesn't matter. Whatever's on the other side, there's an even number, so you don't have to turn over 4. 7, you would have to turn over. So you definitely have to turn over E, you definitely have to turn over 7, and depending on how you look at things, you might have to turn over K. The reason I'm doing this before going into the details of the pirate riddle is you have to be very clear on what you're doing. You have to be very clear on what's being done, and it is very easy for people to accidentally assume things. So here is the pirate riddle. There are 5 pirates named 1, 2, 3, 4, and 5, right? And they could have been named, Alice, Bob, Charlie, Dave, and Ebert, right? You want things that are easy to quickly look at and understand what's going on. They must split 100 gold coins, and you can't split a gold coin. You can't take slivers. You either get a whole coin or you don't. The lowest named pirate who is still alive proposes a division. And it matters a little bit how you vote, so I will say, I'm going to give you the voting rules. You discuss as long as you want, and then you say, okay, is everybody ready to vote? This vote is going to count. You write your vote on a piece of paper. Nobody else can see it. You put it in a box. And then once all 5 are in there, then you open it up and you don't get to see who voted what. You just get to see what the votes were. You get to see how many yeses, how many noes. If 50% or more people vote for the plan, then the plan passes and you do that division. If over 50% vote against the plan fails. The proposer walks the plank and dies, and the lowest named surviving pirate proposes a plan. Repeat until a plan is accepted. Okay? Assume the pirates are intelligent, right? These are mathematicians, okay? Maybe a physicist or computer scientist as well, but smart pirates, steeped in the world of logic, okay? How do you think the 100 gold coins will be distributed? We're going to talk about this on Tuesday's class. Right now, I just want to make sure everybody understands the game. You have 100 gold coins, pirate 1 proposes. If the plan is not supported by a majority, by at least 50%, the plan fails and pirate 1 dies, and then pirate 2 will propose. If their plan gets at least 50%, it passes. If not, pirate 2 dies and 3 proposes, and so on and so on and so on. Do you have a question about? Okay.
So does the person who's proposing the plan count as like a vote?
Yes. So you can vote for your own plan. What do you think every plan is going to have at least 1 supporter? Right. Who do you think is going to support the plan that's proposed? The one who proposes, yes. I actually did have a situation where I had a student who asked me to fail them in a class. Because I was at a school where if you fail, the class doesn't show up on your transcript. But if you get a D, it does. And they were afraid that they would pass the course with a bad grade. So they said they would rather fail the class than risk my grading the final. So sometimes you can have strange situations be weird, but yes, it's a good question. You are not removed from the voting. So you get to vote for your own plan if you want. And almost surely you want. Okay. They're not suicidal pirates. What do you think? Well, no, I don't want to color you too much. So is this a question about the mechanics of the game?
Yes.
Okay, what's the question?
So the final division, what do you mean by that?
So what I mean is, I've got 5 pirates. Who's alive, who's dead, who has how many coins?
Okay,
So I want you to tell me what you think will be the division.
So I need to tell the number of pirates and the share of gold.
Yes, right. So, you've got intelligent pirates, I want you, and you can talk amongst each other, you can play with friends, and try to get a sense of what do you think will happen? Does everybody understand the game?
So for proposals we've passed, only about 50% is, if it's exactly.
If it's exactly 50% pass, and again, the game is very different if 50% is not enough to have it pass.
Oh, it's more than.
No, it's no 50% or more, it passes. Over 50% against and it fails. So think of it as the tie goes to the proposal. You know, if it's tied, then whoever proposes it wins. Okay, any questions about this? All right, so I'm going to end today's lecture.